So welcome. This is day 6. So we're going to talk about bonds, molecules, and moles. Before we start, I first just want to say you guys are doing great. Every day that we've done in this class is like at least a week in a high school chemistry class. So y'all are learning a lot really fast, and you're doing a really good job. I've been really impressed with the problem sets everyone's been turning in. Also, thank you to everyone who filled out the week 1 check-in. If you haven't filled it out, I'd really appreciate it. One sort of common theme was that people wanted more review of bonds, and people were confused by how to draw chemical structures, which is exactly what I would have expected since that's the most recent thing we talked about. So I'm going to review some of that today. But yeah, I think that's everything I wanted to say before we start. So we're going to start with a review of bonds and why they happen before we talk more about, molecules and how we use them. Okay, so the valence electrons are the outermost shell or the highest energy level electrons in an atom. And because they're sort of the outermost shell, that is the shell of electrons that any other atoms are going to see and interact with. So the valence electrons are really important for determining how many bonds an atom wants to make and how it wants to act. So in order to understand bonds, we really need to understand valence electrons. So the steps for figuring out the number of valence electrons, there's 2 ways of doing it. First is by filling all of the orbitals explicitly. So first, we need to figure out the total number of electrons that's equal to the total number of protons, which is the atomic number. So the number above an element on a periodic table. And that's the number of protons. And for an element or an atom where the charge is 0, the number of protons equals the number of electrons. And then our orbitals we can think of as little shells that each can hold 2 electrons. And we're going to fill from the lowest level first, and then within a sublevel, so like this 2s sublevel or this 2p sublevel, we're going to fill 1 electron in each shelf in that sublevel before any of the orbitals or shelves gets a second electron. And then the valence electrons are the ones in the highest level that has any electrons at all. And again, we're just talking about the main group elements. So for hydrogen, there's 1 electron, it is a valence electron. And there's 1 valence electron, no core electrons. So core electrons are any electrons that aren't the valence electrons. There are none of those here. Helium has 2, it has a full valence shell. Then when we move on to lithium, we have 3 electrons. So now our second level is our valence shell. We have 1 valence electron. There are 2 other electrons that aren't the valence electrons, so there's 2 core electrons. And so as we keep adding electrons, we're filling it like this. Okay, so that is sort of the order of filling the orbitals. You guys did a really good job with that on the problem sets, but I just wanted to go over it one more time. So does anyone have any questions on orbital filling? Okay. So this is useful because these orbitals are important. But if all you need is the number of valence electrons and you don't care about 3s versus 3p or anything like that, you also, for the main group elements, can just get the number of valence electrons off the periodic table. So this first column has 1 valence electron, 2 valence electrons, and then 3, 4, 5, 6, 7, 8 on the other end of the table. So if anyone ever asks you for the number of valence electrons in rubidium, I highly recommend that you just look on the periodic table and not try to draw, 37 electrons. So this is sort of the shortcut if all you need to know is the number of valence electrons. Okay. So we're going to talk about covalent bonds today, but we talked about ionic bonds at the end of day 5, so you can go back and review that if you want. But sort of the core idea for both, for any kind of bonding, anything that has to do with electrons, is we can see how full our Lewis dot structure is. So we can see how full our valence shell is by drawing Lewis dot structures, which you also practiced on the homework. And atoms want full valence shells. Full valence shells are stable. And so if you look at the periodic table, this 8th column has all of these elements will have full valence shells when they're neutral. And so those are called noble gases. They're very stable. They don't want to react with anything else because they're already happy. They have a full valence shell. And all of the other elements aspire to have the same level of stability. So they're all going to try to get rid of electrons or acquire more electrons or bond and share with friends in order to have a full valence shell, which for everything other than hydrogen means 8. So because hydrogen's valence shell is its first level, it wants 2 valence electrons because that would be a full first level, that 1s orbital being full. But then for everybody else in this main group, they will want 8 valence electrons. Okay, so that is kind of why bonds happen. So a carbon atom with no bonds and that's neutral will have 4 valence electrons, and it wants 8. A hydrogen atom that is neutral has 1 proton, 1 electron, so it has 1 valence electron, and it wants 2. It wants that full valence shell. And so hydrogen and carbon can make a deal where each hydrogen has only 1 electron that it can share, and it wants to share, to find somebody else that has 1 electron that it can share with it. So we're going to need 4 hydrogen atoms per carbon atom to make each of them happy. So this will have 4 single bonds. So a single bond involves 2 shared electrons. So we can always look at this valence shell and say, carbon wants 4 bonds. It needs 4 friends that will each loan it 1 electron. Hydrogen wants 1 bond because it just needs 1 extra electron. So carbon will always want 4 bonds, and hydrogen will always want 1 bond. So yes, exactly. So someone asked, the 2 dots represents a line. Yeah, that's exactly right. So when we get to how we draw these compounds, I'm showing the full electrons right now, but a single bond is 2 electrons shared. So anywhere there's 2 electrons here, that would just be 1 bond, 1 line, single bond. A double bond is 4 electrons shared, so it's just like 2 single bonds, so 2 lines, and a triple bond would be 6 electrons shared. So a double bond you can think of like 2 single bonds. So a carbon needs 4 bonds. It could also have 2 double bonds, or 1 double bond, or sorry, 1 single bond and 1 triple bond. So it needs like 4 total electrons from friends. Does this make sense? So the key thing to remember is carbon wants 4 bonds, hydrogen wants 1 bond. In general, with all elements in the main group, we can figure out how many bonds they want based on how many valence electrons they have, which we just went over how to figure out how many valence electrons they have. Do we feel okay about bonds? Cool. Okay, so with writing compounds, we can call this CH4. So we have 1 carbon and 4 hydrogens. So this little subscript 4 tells us that we have 4 hydrogens. So one of the main points of confusion always when I teach this, and for you guys as well, based on your feedback, is how to deal with these simplified drawings. And we talked on Friday about how to look at a simplified drawing and figure out what it is, but we didn't actually go the other direction. And one of you asked about that, which is a really good point. So this is a full drawing of a molecule. And so you can see we have 1, 2, 3, 4, 5, 6, 7 carbons. We have a lot of hydrogens. You can just count all the H's. We have a bromine, we have an oxygen. We have a whole bunch of single bonds. So anywhere that you see 1 single line, that's a single bond. And we have 1 double bond right here. So I think when it's all drawn out like this, people tend to be okay with interpreting that. So each of these single bonds is 2 electrons. This double bond is kind of like 2 single bonds, and so it's 4 electrons. Does anybody have any questions about what this molecule is or how to read this? Okay, so if we're simplifying a full drawing, the first thing we're going to do is we're going to remove any bonds to hydrogen and all of the hydrogen atoms themselves. So for example, up here, we had 3 bonds to hydrogen, and we can remove those because we know that carbon wants 4 bonds. And so we'll just know that there must be 3 hydrogens there in order for the carbon to have 4 bonds. So we can do the same thing for this CH3 over here. And then on all of these 3 carbons in the middle, there's 2 hydrogens. And so we can remove all of those. And then for this carbon right here, it only has 1 bond to hydrogen, and we remove that. So that's step 1, is we get rid of all of our hydrogens. Then the next thing we do is that we remove all of the carbon atoms, but we leave those lines. We leave the bonds between the carbons. So that will look like this. And so we know that wherever a bond is drawn, but we don't see where that bond ends, we know it's a carbon. So there's a bond right here that has no letters. We haven't indicated what atoms there are. And because we haven't indicated it, we know that it must be carbon. So there has to be a carbon here and a carbon here. So if we go back, we know that all of these must be carbons. And then any elements other than carbon and hydrogen, we don't do anything, we leave them. Because if I removed this bromine, how am I ever going to know that it was a bromine, right? If I covered up this bromine, then I'm going to assume it's a carbon. That's the rules, right? So we're going to leave this bromine and this oxygen. So we're only removing carbons and hydrogens. And then the last thing I wanted to, so if you were trying to simplify that line drawing, you're done. This is the simplified drawing. I just want to show you sometimes if people want to emphasize a certain group, they might, like in this case, still draw out those CH3s. That's not like a rule that like, oh, you always like leave the CH3s in this instance. You just might see some people do it sometimes. So you should be able to see this drawing and interpret it. But this is the same as this. So just don't panic if you see a drawing somewhere where someone has left a few random carbons or hydrogens on there. So does anybody have any questions on the rules, on how to interpret this, on how to simplify full drawings into line drawings? So all carbons always want 4 bonds. So these 2 carbons have 3 hydrogens. These 3 carbons right here already have 2 bonds, so they need 2 more. So they'll have 2 hydrogens. But then this guy right here has 3 bonds, 1, 2, 3. So it has 1 hydrogen. To make up 4 total. Any other questions on this? Okay, I'm gonna make you practice. So, yes, exactly. Only hydrogen and carbon atoms will disappear. Okay, so just take a minute. This is a molecule, and if you have pen and paper, you can decide to draw out the full structure, or you can just do it in your head, whatever works for you. But I'm going to ask you, how many carbons are there and how many hydrogens are there in this molecule? I'll give you a minute. Yes. So these are all single bonds around the edges. And then where there's 2 lines, that's always a double bond. So this carbon right here has 1 single bond and 1 double bond. So it has 3 total bonds shown. So that's maybe a hint of how many it wants. Okay, so people seem pretty confident about the number of carbons. So you're right, there are 1, 2, 3, 4, 5, 6 carbons. Anywhere that a bond ends without us showing what atom it is, that's a carbon. And then the hydrogens are a little more confusing. So this carbon right here has 1, 2 bonds coming off of it. So it has 2 bonds already. It wants 4. So it has to have 2 more bonds that are going to both be hydrogens. And so all of these carbons are the same deal. They have 2 bonds and they want 2 more. This carbon on the right has 1 single bond coming off of it and 1 double bond coming off of it. So it has, you can think of that as like 3 bonds already shown, and it wants 4. So it needs 1 more hydrogen that isn't shown in order to make it happy, in order to make it have 4 bonds total. So yeah, so most people think that there's 10 hydrogens, but there's a variety of answers here. So this is something that it just takes practice to look at these line drawings and be able to interpret them. And I'll, on the problem set 6 that's assigned today, there's a lot more practice on this. So just to go over the answers. So anytime there's a single line, that's 2 electrons shared. 2 lines is a double bond, that's 4 electrons shared. Wherever a bond ends without specifying what element it is, so there's an actual bond drawn, but just no letter to show the element, that's carbon. And then wherever carbon doesn't have enough bonds, we add enough hydrogens to make it have 4 total bonds. So our complete line drawing would look like this. So each of these carbons that only has 2 lines drawn gets 2 hydrogens. And over here, there are some carbons that have 1, 2, 3 lines already drawn to them. So they get one more hydrogen. And so this is C6H10. So there are 10 hydrogens if you just go around and count the number of hydrogens. Does anyone have questions on this? Okay. So yeah, I think often people know the rules and can sort of follow along when I do it like I just did, but it just takes practice. So I'd highly recommend, I think it's the first half of problem set 6 has a lot of practice on this. I would highly recommend just going through that and getting a little more comfortable with these line drawings. Okay, the other concept I wanted to review today, because it's going to come in the second half of the class today, is how we do unit conversions. So if we have a conversion factor, for example, 1 minute is 60 seconds, or 1 kilogram is 1,000 grams. In the same way that 2 equals 2, and so 2 divided by 2 is 1, if we divide either side of this 1 minute equals 60 seconds by the other, we're going to get 1. So 1 minute divided by 60 seconds is 1, or 60 seconds divided by 1 minute is 1. So if we need to convert units, so we need to convert, let's say, 2 minutes into seconds, we don't want to change the actual amount of time that we're talking about, but by multiplying by 1, we are not changing the amount of time represented, we're just changing the units. So we have minutes and we want seconds. So we need the minutes to cancel out. And so we want minutes to be on the bottom. So if we have 2 minutes and then 60 seconds divided by 1 minute, then the units of minutes will cancel out and we'll end up with 120 seconds. So this is just a general, rule of how I do unit conversions. I never think about like, oh, I always multiply by 60 or divide by 60 because I don't like memorizing stuff. I like to just have a method that will prove to me that my units have canceled out and I've ended up with the units that I want to do. So there were some questions on the week 1 check-in about how to do unit conversions. I hope this helps a little bit, but we'll get more practice with it later today. Okay. So when we're talking about counting molecules or units that are relevant for molecules, I just want to remind you, this is a table that I showed, I don't remember on what day, but when we were talking about subatomic particles. So we have electrons that have a -1 charge, protons that have a +1 charge, and neutrons that are neutral. If you remember, we defined atomic mass units as approximately the weight, the mass of a proton or a neutron, because they weigh about the same. And just as a reminder, these electrons weigh basically nothing. So we're not going to really think about them when we're talking about mass. And so 1 atomic mass unit is about 1.67 kilograms. So if I have 1 gram of protons, how many protons do I have? So this math is kind of a, they're not easy numbers to work with, like 2 and 60, like 2 minutes and 60 seconds or whatever. But the concept is the same. So if I have 1 gram of protons, I know the mass of protons in kilograms. So first I'm going to convert from grams to kilograms. So there's 1 kilogram equals 1,000 grams. So now those grams will cancel out. And then I know the mass of a proton in kilograms from this table. So 1 proton weighs 1.67 times 10 to the minus 27 kilograms. Those kilograms will cancel out. And that, if I just plug this into my calculator, 1 gram of protons has 6.022 times 10 to the 23rd protons in it. Does anyone have any questions on how I did that or where that came from? We'll talk about why this number is important in a minute, but do we feel okay about the unit conversions and the counting? Okay, as always, please send a chat or raise your hand if you do have a question. So this number is kind of like a unit. So 6.022 times 10 to the 23 is the same as a mole. So 1 mole of things means 6.022 times 10 to the 23rd of those things. So just like I would say, I can think of like 1,000 as an amount of stuff. A mole is just 6.022 times 10 to the 23 of whatever thing it is. So if I have 6.022 times 10 to the 23 protons, that's the same as saying I have a mole of protons. So a mole is just like a number of things. So this number we call Avogadro's number, and it's sometimes written as N sub A. So there's a question about how I did this unit conversion. I just did 1 divided by 1,000 divided by 1.67 times 10 to the minus 27, because these are on the bottom. So what I would actually plug into my calculator is 1 times 1 over 1,000 times 1 over 1.67 times 10 to the minus 27. So I'm just setting up these fractions to get my units to cancel out. And then just plugging the math into my calculator. Does anyone have any questions on like conceptually what a mole is or what Avogadro's number is? So Avogadro's number, 6.022 times 10 to the 23, we use all the time. I don't think you need to sit down and memorize it, in part because early on in your chemistry classes, it will be given to you, and then eventually you will use it so much that whether you like it or not, you'll memorize it by accident. So I never sat down and, repeated this number 20 times to myself. I just used it enough that, eventually I remembered it. So don't sit down and memorize it, but you will use it all the time. And definitely don't memorize these masses. But if I tell you Avogadro's number, you should be able to use unit conversions to figure out what it means, what the mass of a proton is. Questions on moles? Okay. So what we just figured out is that 1 mole of protons weighs 1 gram. We also know that 1 proton weighs 1 atomic mass unit. Those are both just straight from this table. So 1 proton weighs 1 atomic mass unit, and we just figured out that 1 gram of protons has 1 mole in it. So a mole of protons weighs a gram, and 1 proton weighs 1 atomic mass unit. And we also know that a neutron weighs the same as a proton. So also 1 mole of neutrons weighs 1 gram, and 1 neutron weighs 1 atomic mass unit. So if I have 3 protons and 3 neutrons, the total mass will be 3 atomic mass units. And if I have 3 moles of protons and 3 moles of neutrons, the mass will be 6 grams. Do we feel okay about that? I'm going to show you an example of why this matters in a minute. Okay. So let's look at neon. I think I'm going to ask you a bunch of questions. Some of these you should already know how to answer from like day 4 or whatever that was. So how many protons does neon have? But then we're going to talk about the masses. So I'm just going to pop this poll up that asks all of these questions. Yeah, I'm not going to give you a hint yet. I'm just going to give you a second to go through these and see if you can think about how many protons does an atom of neon have? How many neutrons does 1 atom of the most common isotope have? How much does 1 atom of the most common isotope weigh? Or what is its mass? And then the same questions, yeah. I'll shut up now. I'll give you about another minute to think about it.
Wait, is 4 and 5 supposed to be different answer? Because they're all the same answers, 10, 10.18, 20, 20.18.
So
is that right?
We'll go over the actual numeric answers in a minute. But just I'll give you a hint, which is that if 1 mole of protons weighs a gram and 1 proton weighs 1 atomic mass unit, then if you know the mass of something, the mass of a mole of something in grams, then the mass of 1 of that thing in atomic mass unit should be exactly the same. Okay, I'm going to turn the poll off and we'll go over it. So the first question is, how many protons does a neon atom have? I think almost all of you got this right. That's just the atomic number straight off the periodic table. Nothing has changed on that. So we talked about isotopes, I think on day 4. I don't know, all the days have run together. So the average atomic mass of all of the isotopes based on their abundance, based on how many of each isotope exist in the world, is 20.18. The most common isotope then has a mass of 20. So one atom has to have a whole number of neutrons. We can't have one atom that has 10 protons and 10.18 neutrons. We can't have 0.18 of a neutron. So the most common isotope of neon has an atomic mass number of 20, and it has 10 protons. So 20 minus those 10 protons is 10 neutrons. So the most common isotope has a mass number of 20, and so it has a mass of 20 atomic mass units. So the answers for those first 3 need to be whole numbers because we're talking about one atom. But now we're moving to the average. So how much does one neon atom weigh on average? So if I take all of the neon atoms in the world and average their mass, I'll end up with 20.18 atomic mass units. So that is what this number on the periodic table means. I've taken all of the atoms of neon that I could find in the world, and the average mass will be 20.18 atomic mass units. And then this was the question that was asked. That is the same as saying, if I take a mole of neon atoms, so a whole bunch, 6.022 times 10 to the 23 neon atoms, it will weigh 20.18 grams. Does anyone have any questions on where I got these numbers or why this is true? And so this comes back to the importance of isotopes that we were talking about before, is that, most neon atoms I find will have a mass number of 20, so they'll have 10 neutrons. But a decent number will have 11, some will even have 12, so that the average is 20.18. Yeah, so number 4 is, on average, how much does one neon atom weigh? Anytime you see like either the word average or 1 mole, average means I've taken 1,000 or 1,000,000 or a whole bunch of neon atoms. I've weighed each of them and I've taken the average. And so that no longer needs to be a whole number because it's on average over all of these. And I read that number off the periodic table. And that is in atomic mass units because that's the average mass of one atom. So it should be a small number. Atomic mass units are 10 to the minus 27 kilograms. But then if I have 1 mole of neon atoms, its mass in grams will also be 20.18 grams, because 1 mole of protons or neutrons or both weighs 1 gram, and 1 proton weighs 1 atomic mass unit. So yes, in response to the question in the chat, if you pull this number off the periodic table, it is both the average mass of 1 atom of that element and the mass in grams of 1 mole of that element. So this is not a coincidence. We defined atomic mass units and moles, that Avogadro's number, so that this would be true. That is where those numbers came from. So very rarely in science, and even more rarely in like practical engineering stuff of building bridges, or designing pharmaceutical molecules or anything like that, you're not going to have one atom of stuff. We're almost always working in bigger numbers, like grams of stuff, moles of stuff. And so most commonly, you'll be answering this last question here. You're not going to have one atom of anything. You're going to have a whole bunch of atoms that have the average composition of isotopes. Does this make sense? I'm going to make you practice a lot. So if it doesn't make sense, it will. So I wanted you to understand where these numbers come from, and the difference between atomic mass units for the mass of one atom and grams for the mass of moles of atoms. But in practice, you can just read these numbers off the periodic table, and 1 mole of neon atoms will weigh 20.18 grams. So the molar mass, which is something you're going to have to calculate a lot, is how much in grams does 1 mole of our molecule weigh? So the molar mass of neon is 20.18 grams per mole. So 1 mole of neon weighs 20.18 grams. The molar mass of neon is 20.18 grams in a mole. So I'm just going to give you some examples. So this is hydrogen and oxygen from the periodic table. So the mass of 1 mole of oxygen atoms is 15.999 grams, and the mass of 1 mole of hydrogen atoms is 1.008 grams. So this is just exactly the same thing we were doing with neon. On average, 1 oxygen atom will weigh 15.999 atomic mass units, and 1 mole of oxygen atoms will weigh 15.999 grams. So those numbers are the same. So if I have 2 different molecules, so this is H2O or water, and this is O2 or elemental oxygen, 1 mole of H2O molecules has 1 mole of oxygen atoms and 2 moles of hydrogen atoms, in the same way that 1 oxygen molecule has, 1 H2O molecule has 1 oxygen atom and 2 hydrogen atoms. So to get the molar mass, I'm just going to take 15.999 plus 2 times 1.008. So the molar mass of water, or H2O, is 18.015 grams per mole. For oxygen, O2, 1 oxygen molecule has 2 oxygen atoms. And so what that will mean is that 1 mole of O2 molecules is the same as 2 moles of single oxygen atoms. And so our molar mass will be 31.998 grams per mole, because I've just taken this 15.999 times 2. Does this make sense, how I did that?
So for the molar masses, we use the 15 point, because they both have, because in like sig fig, in significant figures, it's like 4 significant figures. That's why it would be like the 8. Okay, it makes sense. I get it now.
Okay. Yeah. Answered your own question. So I just want to review one more time what a mole means. A mole is just a number of stuff, in the same way that I could have 1,000 molecules, I can have 10,000 molecules, I can have a mole of molecules. It is a way of counting things, not a mass of things, which is why we need this conversion factor to convert between grams and moles for a given molecule. So if I have 1 mole of H2O molecules, I have 6.022 times 10 to the 23rd H2O molecules. And if I have 1 mole of O2 molecules, I have 6.022 times 10 to the 23rd O2 molecules. But if I have 1 mole of H2O molecules, I have 1 mole of oxygen atoms and 2 moles of hydrogen atoms. So I have 3 atoms per molecule. So does that make sense? A mole is just a count. Okay. So just to check your understanding, I have 3 questions here. To answer the question in the chat, you use that Avogadro's number when you want to convert between number of molecules and number of moles. When you're just converting between mass and moles, you don't need Avogadro's number. You just need these molar masses from the periodic table. So the questions are, which weighs more, 1 mole of H2O or 1 mole of oxygen? Which contains more atoms, a mole of H2O or a mole of oxygen? And which contains more total molecules? Yep, H2O is 18.015 grams per mole, exactly. And O2 is 31.998 grams per mole. I'll give you about 30 more seconds. So 1 mole is 6.022 times 10 to the 23rd things. So 1 mole of H2O molecules will be 6.022 times 10 to the 23rd H2O molecules, and 1 mole of O2 molecules will be 6.022 times 10 to the 23rd O2 molecules. So if you're ever confused about like the concept of a mole, just substitute in 1,000 for 6.022 times 10 to the 23rd. So which has more mass, 1,000 water molecules or 1,000 O2 molecules? Which has more atoms, 1,000 of these or 1,000 of these? And which has more total molecules, 1,000 of these or 1,000 of these? It's the same concept. Okay. So this is a little tricky, the third one especially. So let's go over it. Which contains more mass, a mole of H2O or a mole of oxygen? Well, 1 mole of H2O weighs 18.015 grams, and 1 mole of O2 weighs 31.998 grams. So the oxygen, the O2 weighs more. 31.9 is bigger than 18, right? Which contains more atoms, a mole of H2O or a mole of oxygen? Well, each H2O molecule has 3 atoms, and each O2 molecule has 2 atoms. So if I had 1 molecule of each, I have more atoms in H2O than in O2. If I have 1,000 molecules of each, I'll have more atoms in H2O than in O2. And so the same is true for a mole. So there will be more atoms in a mole of H2O than in a mole of O2, because there are 3 atoms per molecule in H2O and 2 atoms per molecule in O2. Okay, so the last one is a little bit tricky. Which contains more molecules, a mole of H2O or a mole of O2? Well, this is one molecule and this is one molecule. If I have 1,000 of these and 1,000 of these, I have the same number of molecules in both piles. If I have 6,000 of these and 6,000 of these, I have the same number of molecules in both piles. So if I have 6.022 times 10 to the 23 of these, and 6.022 times 10 to the 23 of these, I have the same number of molecules in both piles. So those will be the same. So I'm just using 1,000 as like an example because a mole is just a number. So a mole is 6.022 times 10 to the 23rd. Things. So if I have a count of molecules, I know how many molecules I have. I'm going to divide by 6.022 times 10 to the 23 to figure out how many moles I have, or vice versa. So the difference between an atom and a molecule, an atom is the smallest unit of a given element. So you could have a hydrogen atom, an oxygen atom, and a hydrogen atom. So this is one oxygen atom bonded to 2 different hydrogen atoms. A molecule is the unit of those things bonded together. So this is one H2O molecule. This is one O2 molecule. So when elements are bonded together, they become a molecule. And so one H2O molecule has 3 atoms in it, and one O2 molecule has 2 oxygen atoms in it. And so a mole is just a count of molecules. So if I have one H2O molecule and one O2 molecule, I have 3 atoms in my right hand and 2 atoms in my left hand, because there's 3 atoms per molecule in H2O and 2 atoms per molecule in water. But if I have one molecule of H2O in my right hand and one molecule of O2 in my left hand, I have the same number of molecules in both hands. I have one water molecule and one oxygen molecule. So if I have a mole of water molecules in one hand and a mole of oxygen molecules in the other hand, I have the same number of molecules in each hand. So a mole of stuff is just a count of the number of units of that stuff that I have. Does that help? Cool. So I'm going to make you practice finding molar masses because you're going to have to do it a lot and you better get comfortable with it. So just as a reminder, the way that I calculated the molar mass here is I read off the molar mass off the periodic table of each atom. So this H2O molecule has 1 oxygen atom and 2 hydrogen atoms. So I have 1 mole in 1 mole of H2O molecules, I have 15.999 grams of oxygen, and I have 2 moles of hydrogen atoms, so I have 2 times 1.008. So I have 1 oxygen and 2 hydrogens. So I took 15.999 plus 2 times 1.008. Okay. So using the periodic table, I can send the link to that in the chat if you want. I will stick it in the chat now. I want you to calculate the molar mass of these molecules. And I'm going to stick you into groups. I would like you to actually work together in your groups for 2 reasons. If this is confusing and you're struggling with it, then your group can help you. If it's easy for you, I promise you'll understand it better when you try to explain it to someone else. It happens to me all the time that I think I know this stuff well. And then as I'm making the slides, I'm like, oh, how do I explain this clearly? Do I really understand it? So you'll learn it better by trying to explain it to your classmates. So I'm going to send you into breakout rooms. I'll give you about 5 minutes maybe. And then I will pull you back. But yeah, I mean, I know not all of you are able to turn on your cameras, but do try to work together and talk through these in your groups. So go ahead and accept those invitations if you haven't already. I'm going to pause the recording. Those of you who are watching this later, I still would really recommend that you pause this and practice if this is something that's new to you. Okay, I think everybody's back. So I'm just going to go over how we do this. So for hydrogen, for H2O, we have 2 hydrogen atoms and 1 oxygen atom. From the periodic table, we can get the molar masses of each of those elements. So we do 2 times 1.008 plus 15.999 equals 18.015. So that's the example that we had on the previous slide. For Na and Cl, we again just get those masses from the periodic table. So we get 58.44. For C6H6, we have 6 carbon atoms that each weigh 12.001 grams per mole, and 6 hydrogen atoms that each weigh 1.008. So we just plug that into our calculator and we get a total of 78.114 grams per mole. For KOH, we have potassium, oxygen, and hydrogen. So we add those up and we get 56.105. And then the last one, I just put this on here to show you that it doesn't matter how big a molecule is, you just follow the same formula. So we have 11 carbon atoms that each weigh 12.011, 12 hydrogen atoms that each weigh 1.008, and 1 nitrogen atom that weighs 14.007. So just as a reminder, we got those atomic masses from the periodic table. And we're just counting up how many of each type of atom or how many of each element that we have. How did this go? Do people feel okay about calculating the molar masses? Okay. Cool. So converting between mass and moles is going to be really important. So I'm going to have you practice with that in a minute. If the atomic mass unit, if it has multiple numbers after the decimal, it's fine. We just use it like it is. And then we just apply our sig fig rules to figure out how many decimal points to round it to. Okay. So to convert between mass and moles, I'm just going to use an example. So you know how to find the molar mass. So the molar mass of O2 is 31.998. It's 2 times 15.999. What that means is that for oxygen, we have a conversion factor, 31.998 grams equals 1 mole. And so in the same way that we had 1 minute equals 60 seconds, we can have 31.998 grams per 1 mole, or 1 mole per 31.998 grams. So those two fractions, because 31.998 grams and 1 mole is the same for O2, those two fractions are both 1, they're both the same. So if I want to convert from moles to grams, then I want my moles to cancel out, and I'll use this one. So my grams are on top. If I want to convert from grams to moles, I'll use this one so that my 2 grams will cancel out and I'll end up with moles. So I really don't want you to memorize anything ever, but in this case, I don't want you to memorize, oh, here's when I multiply by the molar mass and here's when I divide by the molar mass. If you just know that the molar mass is grams per mole, then you can flip it upside down to get moles per gram to do the conversions. Does this make sense? So don't try to memorize, here's when I multiply by 31.998, and here's when I divide for oxygen. You just want your units to cancel out. Okay. So I'm going to send you back in your groups to practice. And these are the same molecules you have before, so you should already have the molar masses. And so I want you to convert this number of moles of each compound into mass. So convert 4 moles of H2O to grams, and so on. Okay. And again, please actually work with your groups, check your answers with each other. Okay, welcome back. So let's go over the answers to these. So we're trying to convert moles to grams. So we want the moles to go away and cancel out, and we want to end up with grams. So we want grams on top and moles on the bottom so that our 2 moles will cancel out. So our molar mass of H2O was 18.015 grams per mole. So 4 moles would be 72.1 grams. So we're going to do exactly the same for all the other ones. For NaCl, we have 58.44 grams per mole. The moles cancel out. We end up with 584 grams. For C6H6, our molar mass was 78.114. So we're going to end up with 7.81 grams. For KOH, our molar mass was 56.105, so we'll end up with 842 grams. And then the last thing is C11H12N. Our molar mass from the previous slide was 158.22 grams. So we're going to end up with 15,800 grams, which if you want, you can convert to kilograms. So this is 15.8 kilograms. Any questions on this? Okay. So we can also use our molar mass to go in the other direction. So if we want to convert grams to moles, now we want our grams to cancel out. And so we want to have moles on the top. I got a question on how we decide how to round. We use our significant figures rules, like we talked about on whatever day that was. So in this case, I have 3 sig figs here and 5 sig figs here. Because I'm multiplying, I want to have my answer be rounded to 3 significant figures. So 15,800 or 15.8. Okay, so last group thing for today. I want you to convert these masses to moles. So now I want my masses to cancel out So I want my mass on the bottom. And so for this first example, I still have 18.015 grams per mole, but I've flipped the fraction. So now the grams are on the bottom and the moles are on the top. The grams will cancel out and I'll end up with 2.89. So I'm going to send you into your groups to do the practice with the other ones. Just give it 30 seconds for people to cycle back in. Okay, I think everybody's back. So like I said, we want our grams to go away and end up with moles. So we're going to put our grams on the bottom and moles on the top. So for all of these, we're just going to end up dividing by the molar mass that we found a couple slides ago. But again, don't try to remember to memorize like when to multiply and when to divide. Just use this method of making the units you want to go away cancel out. So 107 divided by 58.44 is 1.83 moles. Here we have kilograms. So I hope you guys noticed that we need to convert from kilograms to grams and then grams to moles. So you're going to end up with 19.2 moles. So I didn't show it on the slide, but there's an extra 1,000 in there. That's why you end up with 19.2. And then 527 divided by 56.105 is 9.39 moles. And then the last one is 1 gram divided by 158 grams per mole, gets us 0.00632 moles. Questions on these conversions? Okay. So the last thing I want to mention briefly is just to go back to using that Avogadro's number. You know how to convert from mass to moles, we just did it. And we also know that 1 mole is equal to 6.022 times 10 to the 23rd molecules. So if I wanted to know how many molecules are in, for example, 0.5 grams of oxygen, I would convert my grams to moles using my molar mass so that those grams cancel out. And then I would convert my moles to molecules using Avogadro's number. So 1 mole is 6.022 times 10 to the 23 molecules. Those moles cancel out and I end up with 9.4 times 10 to the 21 molecules. So there'll be more practice with that on the last problem of problem set 6. Okay. So this is why it was so important for us to learn those unit conversions, because we're going to use them a lot in situations like this. Okay, so that is it for the day, but I'll stay after if anybody has any questions.